What do all these places have in common? Sense input, and lots of it. Well, what creates sense input? Sorry if I'm scaring any empiricists out there. It's all fun and games to consider experience as the source of knowledge, but what is the source of experience? Is there some sort of substance that gives off sense data? One failure of empiricism is its lack of explanation for substance. Robert Pirsig observes that the first problem of empiricism, if empiricism is believed, concerns the nature of substance. Since all knowledge comes from sensory impressions, and since there's no sensory impression of substance itself, it follows logically that there's no knowledge of substance. It's just something we imagine. Contrasting empiricism, Immanuel Kant presumes the existence of substance by analyzing the appearances of objects. Stating that an object projects some sort of appearance onto our senses implies that it exists outside its supposed appearance. Kant is then able to analyze appearances without giving up the existence of substance beneath the appearance. This is the method by which he deduces universal laws governing appearances of objects, which he summarizes in his Analogies of Experience. Physicists, on the other hand, presume the existence of substance before their work begins. In order to study physical phenomena, its objective validity cannot be in question. With the advent of relativity and quantum mechanical theory in the early 20th century, physicists had to change their conception of substance to agree with new ideas of uncertainty. The question is, then, do Kant's universal laws, created in the time of classical Newtonian dynamics, hold up in light of modern physics? I think yes, if the Copenhagen interpretation of quantum mechanics is accepted and the goal of physics is aligned with Kant's conception of pure natural science. In fact, quantum mechanics serves as an empirical boundary of possible experience of appearances. In this video, I will go over Kant's idea of causality and permanence, and then provide an introduction to quantum mechanics before arguing for their compatibility. Nature, for Kant, does not lie in the reality of objects. We can cognize objects as having two distinct sides: real characteristics and appearances to our senses. Human sensibility can never penetrate the real characteristics of objects, and as such, we can only be concerned with appearances. Kant therefore determines that nature, considered materialier, is the totality of all objects of experience, and with this only are we now concerned. Kant's famous universal laws of nature do not concern objects in themselves, but instead govern objects as they appear to us. Within these natural laws, Kant arrives at three postulates concerning substance, which we must cognize a priori, known as the analogies of experience. They enforce that experience is possible only through the representation of a necessary connection of perceptions. The first analogy states that in all change of appearances, substance persists, and its quantum is neither increased nor diminished in nature. This supposes the permanence of substance. The second analogy claims all alterations occur in accordance with the law of cause and effect. Alterations can be thought of as changes in appearances. Within the world of our sensibility, events must be in relation to causes, and our understanding must presuppose these concepts in order for us to obtain experience of objects in general. Kant simultaneously concludes that nature must universally conform to these laws, at least in the conditions of the possibility of experience. In this sense, natural science is concerned only with nature in accordance with our sensibility. Rerouting one's thinking around this concept entirely changes one's conception of science. For Kant, experience is not the mere perceiving of sense input. Purely subjective perceptions of individuals do not constitute experience. Instead, experience must be universal, i.e., concepts for our understanding give perceptions universality and necessity. Kant does believe that our judgments about objects, as far as the judgments concern them as objects of possible experiences, can be universal. He gives the example of, when the sun shines on the stone, it grows warm, and the sun warms the stone. The former is a supposed judgment of perception, and is not universally valid, but the second is a judgment of experience, and is therefore universal, and necessarily belongs to the sun as an object of experience. However, Kant clearly states if the pure concepts of the understanding try to go beyond objects of experience and be referred to things in themselves, they have no meaning whatsoever. Therefore, the concept of the warmth of the sun cannot be applied to the sun as it exists separately from us, but only as it exists in a system together with our sensibility. Quantum mechanics, as a systematic theory for describing reality, is perplexing to all. It concerns the understanding the smallest particles and lowest energy objects that can be observed in the natural world. As physicist Richard Feynman famously said, if you think you understand quantum mechanics, you don't understand quantum mechanics. The most widely accepted interpretation of quantum mechanics, among many others, is the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. Due to the discovered wave nature of quantum particles, such as the electron, science lost the ability to deterministically predict the location and movement of particles. You may have heard of the Heisenberg uncertainty principle. Essentially, for any measurement tool, including our eye, to measure the position of something, light must hit the object and then enter our eye. However, light has momentum and affects the position of particles. Therefore, our measurement of a small particle, like an electron, actually affects the movement of said particle, which makes deterministic conclusions stemming from the measurement impossible. The Copenhagen interpretation therefore understands physical systems to be probabilistic in nature. We cannot know the exact location of a measured particle except at the time of measure. After the time of measurement, we can only know where a particle could be in the form of a probability distribution governed by Schrödinger's wave equation, which is the equivalent to Newton's second law in classical mechanics. One consequence of this theory that's somewhat understandable, although non-intuitive, is quantum tunneling. We can begin our approach classically. Imagine a ball going over a grassy hill. If the ball is not moving fast enough, if it doesn't have enough energy, it will not crest the hill and will always fall back to its original side. However, if it is moving with enough energy, it will always pass over the hill. The cause is always correlated with the effect in this case. If the ball has enough energy, it will always pass over the hill, and if it doesn't, it will always fall back to its original side. Quantum tunneling is a similar situation. One example is alpha decay, where a heavy nucleus, such as uranium-238, releases a helium nucleus consisting of 2 protons and 2 neutrons, denoted an alpha particle. Due to the strong nuclear force, which is a fundamental force holding nuclides together, this alpha particle should not be able to escape the uranium nucleus. We can equate this strong nuclear force to our grassy hill. In this case, the barrier is not one of physical contact, but it serves the same purpose, which is it stops the alpha particle from passing through. If the particle does not have enough energy to go over the barrier, it should not be found on the other side of the barrier, right? It can't pass over the hill in our analogy. In fact, the wave properties of the alpha particle require a probability of finding it on the other side of the barrier in order to follow the rules of quantum mechanics. In this sense, an alpha particle with a specific energy might or might not pass through the barrier based on a probability distribution determined by Schrödinger's equation. Classically, this is unfathomable. Events with the same cause, the same initial conditions, can possess different outcomes. The alpha particle has a minuscule chance of tunneling through the barrier presented by the strong nuclear force. This effect has been rigorously confirmed experimentally. The question, then, is whether Kant's analogies of experience are still valid as laws governing our understanding of appearances, or if the lack of causal and local relations stemming from quantum mechanics spells the end of Kant. After all, quantum mechanics seems to apply universal judgments of experience that do not follow causality or permanence. How can the analogies survive? For the first analogy, the answer is evident. Mass might not persist, but all of these systems preserve energy. Therefore, if one conceptualizes substance as energy, the analogy is preserved. On the other hand, we must consider that either the second analogy is incorrect or our measurement systems are misleading us, and judgments of quantum mechanics are just judgments of perception. To answer this question, we must return to a famous 20th century debate between 2 pillars of physics, Albert Einstein and Niels Bohr. Albert Einstein was a reluctant founder of modern physics. He was the first to propose quantized packets of light, which eventually led to the quantum revolution, but for his entire career, he did not acquiesce to the causal implications of the Copenhagen interpretation. As he famously said, God does not play dice. More elegantly, in a letter to Max Born, Einstein expressed that the question of causality worries me a lot. Will the quantum absorption and emission of light ever be grasped in the sense of complete causality, or will there remain a statistical residue? Aligning with this sentiment, Einstein is generally portrayed as a realist. Daniel Wojcik asserts that Einstein's goal was precisely to picture the objective reality of any physical system. Since quantum mechanics requires probabilistic behavior, the belief that physics describes reality as it is in itself requires a loss of causality, and Einstein would not give that up. For many years, he searched for issues and devised thought experiments to undermine the Copenhagen interpretation, eventually asserting that along with the lack of causality exhibited in the interpretation, locality must also be lost, which he thought to be impossible. However, recent experimental evidence has essentially disproved Einstein's thought experiments designed to undermine QM. This can be summarized by the EPR thought experiment, which rejects the theory of quantum entanglement predicted by the theory of Schrödinger, where particles are able to affect each other instantaneously over a distance. In this case, the spin axis of two photons are connected, and the measurement of one particle determines the spin of the other. Thus, they are able to interact instantaneously through extended space, violating Einstein's theory of relativity in the causal chain, which he thought to be impossible. This phenomena has more recent experimental evidence showing that photons and even electrons are able to exhibit this spooky action at a distance, as Einstein termed it. Einstein's causality and locality therefore fail in the continuation of quantum theory. Einstein can be interpreted as both entirely opposed to and somewhat aligned with Kant. On one hand, Kant asserts that we cannot know objects as they exist separate from our sensibility, and Einstein's posited goal of physics is directly contrary. However, Einstein tried his absolute hardest to preserve classical causality in the face of modern physics. The second analogy, although embodied by Einstein in regards to objects as they are in themselves, not their appearances, was important enough to him to warrant decades-long fights with his peers. Niels Bohr, on the other hand, is more closely aligned with Kant in his theory of substance. According to Bohr's assistant, he once said, "There is no quantum world. There's only an abstract quantum physical description. It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature." It is easy to directly draw parallels to Kant. However, we must examine his specific perspective. Results obtained from quantum determinations are not intrinsic to the objects due to the issues of measurement. They instead should be viewed as determined by the whole experimental arrangement. In this sense, we cannot separate experimental arrangements from the objects as they appear to us, which prohibits us from separating qualities of the object as it appears to us from the experimental arrangement. Tying these two perspectives together, Bohr understands that physics, as a natural science, must govern nature as it appears to us, not necessarily how it is. And limits on quantum measurement severely hinder our ability to draw conclusions about quantum objects as they appear to us. Bohr is therefore considerably more aligned with Kant. The notion that physics concerns what we know, not what exists, is consistent with Kant's theory of nature and universal natural laws. In predicting quantum states, physicists are precisely stating all they can possibly know about a system, not necessarily the truth of the system or what's going on internally. However, there is still the looming issue of causality. Is Bohr's interpretation compatible with it? Although causality seems lost, as indicated by phenomena such as alpha decay and entanglement, there is still hope. Stephen Palmquist argues that Kant's phenomenal world refers not to physical reality as such, but to physical reality as observable, that is, ordinary observable experiences. Therefore, measurements of quantum mechanics are outside of the realm of ordinary experience, so human understanding cannot realistically stray into the quantum world. In the conclusion of the Prolegomena, Kant provides similar reasoning when considering the existence of the will of a supreme being. The existence of a will rests on our conception of it through sensibility, and a supreme being is not limited by such things. Similarly, quantum objects rest on concepts that are beyond the realm of human sensibility, so we cannot realistically draw conclusions about these objects based on our inner experience. Therefore, the analogies of experience do not necessarily apply to quantum objects, since we can't realistically have sense impressions of quantum objects in themselves. This claim seems a bit hand-wavy to me. Kant did not know about the possibility of quantum objects, but his theory should hold up under scrutiny of new ideas, if it is to be universal. And quantum mechanics accurately predicts experiment, indicating that it should consist of judgments of experience, since our understanding is being applied to these concepts to create a unified theory. However, Palmquist strengthens his claim by arguing that for measurement limitations of quantum mechanics and relativity, being essentially empirical counterparts of the same transcendental boundaries of human knowledge that Kant's principles establish. In particular, Planck's constant on the quantum end and the speed of light on the relativistic end provide physical measurement limits for sense input, which mirror Kant's boundaries of knowledge. In this sense, Kant's belief that we cannot know the nature of things in themselves is now enforced further by physical measurement limits of the appearance of objects. Our inability to determine absolute position for quantum systems is an empirical enforcement of Kant's postulates. When considering Bohr's interpretation of quantum mechanics, it now makes sense that the inclusion of the measurement apparatus within the measurement itself is a part of this issue. Once the objects are minuscule, the apparatus becomes part of the measurement, and we can no longer absolutely experimentally determine all qualities of the appearances of objects. Thus, we are not only limited from knowing objects as they are in themselves, but are also limited from knowing parts of their appearances to us. However, it is important to distinguish that this does not indicate a loss of causality in objects of possible experience. As Palmquist notes, quantum mechanics requires that we cannot causally connect possible states of quantum objects. However, this does not indicate a lack of cause, but instead an inability for human sensibility or measurement devices to discern such cause. The absolute cause and appearance of quantum events might still be lying underneath the measurement barrier of quantum mechanics. Therefore, we cannot legitimately distinguish whether quantum objects do or do not follow a causal relationship, so we cannot realistically conform their movements to the second analogy. Therefore, Kant might argue that quantum theory, while seeming to describe necessity of the appearance of objects, is similar to the existence of a supreme being. We can discern the existence of quantum particles, but we cannot claim to know their behaviors without transcending experience. We are applying concepts of understanding to physical sense input of quantum mechanics, but the issue of measurement, which is a limit on our senses, provides a physical barrier of entry. Then, any conclusions drawn from inference might be considered illusory, in the same way as ideas of pure reason, since they stray beyond the realm of possible human experience. In this sense, the appearances of quantum objects and the actuality of a supreme being exist beyond our possible understanding. Why should we still pursue quantum theory, then, if it is illusory? Kant enforces that the human spirit will ever give up on metaphysical research is as little to be expected as that we should prefer to give up breathing altogether in order to avoid inhaling impure air. Our thirst for unity and knowledge pushes us forward in the metaphysical realm, and it will do the same in the quantum realm. Since the knowledge pursued in quantum mechanics is applicable directly to sensibility, we are always inclined to pursue it in order to systematically unify our world. Continually, it has real world applications that benefit the human condition, such as quantum computing and nuclear energy. To its end, we will not stop pursuing quantum mechanics as reason is driving us towards either a full quantum theory or a more correct theory outside of our current perception.